Hey everyone, welcome back. In this video, we're going to look at a very specific mechanism called a four-bar linkage. This is a multi-body system. It's going to have three moving bodies. What we want to do is we want to analyze the four-bar linkage for, first of all, position, and second, orientation. And then once we have these two things, position, orientation, we can take them and we're going to combine them into what we call the location description. Now, what we're going to see, because this system has three bodies, is we need to keep track of the position and orientation for each of those three bodies. And at the end of it, we're going to have three location descriptions. So if you have a system with 10 bodies, you need to make 10 location descriptions. Okay, let's clean this up and get started. So what is a four-bar linkage? Here's a simple one. Bodies A, B, and C. You can see that body A and body C are both pinned to the ground at pin joints. Imagine that you grabbed body A and you moved it. Well, body A by itself, right, if we cover up B and C, body A by itself is just a pendulum, so it's going to spin. Same with body C. This one's going to spin as well. And it just so happens that the ends, or somewhere along these linkages, A and C are connected via this body in the middle. Now, these all have names. A and C are both cranks. And then B is called a coupler. Now, if I move A, we know that this point, let's say we call the centers of masses points A, B, C, keep it easy, and let's make this joint point D. Point D is going to follow the path of a circle, right? As A spins, D is going to move in a circle. If this is point E, then E will also follow the path of a circle. As A moves, point D is connected to both body A and body B, which means as A moves and D moves, that means it's going to take body B with it. So body B also has to follow in some way the motion of A. Well, when the coupler B moves, that means that point E is also going to move, and that means that C is going to rotate. What you'll find with this system is that if you move A, you make B move, and in turn you make C move. So however I move A back and forth, B and C are in some way going to follow. Now, this mechanism is actually very common. If you just look all around the world, you will see these types of mechanisms. They are in all kinds of machinery. They're in industrial equipment. They're in construction equipment like bulldozers and backhoes and cranes. Also, the mechanism for doors. If you're in a classroom and you look at how the door is attached, sometimes there's a little metal mechanism on top that connects the door to the wall. That mechanism is a four-bar linkage. Now, you might be asking if this is a four-bar linkage and we have bodies A, B, C, then where does this 4 come from? The fourth body is the ground. In this case, the ground is not going to move, right? But you could imagine that these three mechanisms, they could actually be attached to some other structure that is in turn moving. It doesn't actually have to be pinned to the ground. It could be pinned to something else. And that's often what you see in things like bulldozers and cranes. You'll actually see a whole series of four-bar linkages that help control and stabilize each of the joints. Now, sometimes when I do these diagrams, I'm going to draw a little bit of the geometry so that we can see it. Sometimes it's easier, especially when you're doing your homework or on exams. You can, if you want, just do stick diagrams. And each of these sticks represents one of the bodies. So here would be A, there's B, and there's C. All right, so what I want to do is I want to clean this up just a little bit And what we're going to do is we're going to do a 4-bar linkage, and we're going to take these 2 pin joints, we're going to offset them. So in this case, you might say that there's obviously a horizontal displacement, but there is no vertical displacement between these 2 pin joints. Well, let's go ahead and do the more complicated case, and let's just elevate one of these up, just to make it more general. Also, what we're going to do is, so here's my stick drawing. Let's take the coupler in the middle and let's give it some kind of geometry. So let's just do some general shape. There's a point in the bottom left for one pin joint. There's a point in the bottom right for the other pin joint. And also there is some point of interest, and we want to keep track of that point of interest. All right, so let's clean this up, and let's do the location description for this body, or for this system. So here's our 4-bar linkage system. Remember what we want. We want the location description for each body. Where do we begin? If you recall from the previous videos, every single time we work one of these problems, we have to add 2 things to the diagram right at the beginning. The first is going to be a point, a non-moving inertial point. So where on this system should we put that point? Well, remember just a moment ago we talked about how A is going to move, and then B is going to move with it, and then that's going to make C rotate as well. So there is no point on A or B or C that is not moving except these 2 pin joints. Those are good places to put point in. Which one should we put it on? Honestly, either one's going to work just fine. I tend to go left to right, so hey, let's just put it there. Next, we know also there has to be a non-moving inertial frame, a reference frame. Here is direction X hat in, and then direction Y hat in. Next, let's go through and let's put some points on these bodies that we're going to keep track of. We could, if we want to, we could keep track of the centers of mass. We could make assumptions about the geometry of A and B. We could say they're symmetric, etc. Centers of masses are right in the middle. We could make some assumption about this triangular body up here, body B. Right now, we're not doing equations of motion. We're not doing anything with mass or momentum. So right now, it's actually not that important whether or not we keep track of the centers of mass. So since we're just starting and this is the beginning, for now, I'm going to say let's not do the centers of mass. For now, I'm going to say let's put point A right there. Let's put point B there, and then point C is this other joint. Now, does that work for the location description? Remember first conversation we had, if you know the A position on a body, if you know the orientation of that body, and you know its geometry, then you can come back and then you can make judgment calls and you can claim that you know everything about where that body is. So body A is on, point A is on body A. Here is point B and it's on body B. And point C is the pin joint, and that's actually on body C as well. It's shared by both B and C. So I'm going to use point A for body A, I'm going to use point B for body B, and I'm going to use point C for body C. So that works. Next, you have to have a point for every body. You also have to have a frame for every body. So we have bodies A, B, and C. That means we need frames A, B, and C. So how should we orient those frames? These bodies are moving, the frames are going to move with the bodies. And we know that we're going to use these rotating body frames to keep track of position. So we need to put the frames on there in some way that makes sense and is also helpful to us in making our descriptions. There we go. Let this be X hat A, and there is Y hat A. Next, what should we do for body B? Well, by default, usually, I treat the x-axis as kind of the default when I'm doing position vectors from this point to this point to this point. So let's put A to C. There we go. I'm going to call that one x hat B. Y hat B then is perpendicular to it. There's y hat B. Next, C frame. Well, we could, if we want, we could put x hat C pointing this way along the geometry. You could put x hat C going that way along the geometry. Ultimately, as long as it's obvious, right, and as long as you set the problem up correctly, either way is good. So I'm going to do this one. There's x hat C and y hat C. All right. Now that we have all of that, we're not quite done with the diagram. We are going to have to add a few things to it in a bit. But for now, let's start writing down some of our quantities. So we know that we need positions. So what positions should we call out from this diagram? We have points A, we have points B, we have point C. We would like P into A, P into B, and P into C. Let's do the easy one first, into A. A is along the length of body A. It's in the direction x hat A, and this distance from into A is fixed. So that's it's, you know, a part, right? It's been manufactured, and that length does not change. So let's drop some length in here, L1, and I'm going to say that P into A is L1 x hat A. All right. What are we going to do now for the next one? P into B. Well, we want to relate all of these positions back to this non-moving point. So if we want to go to B, as always, we could go through the inertial frame, right? I could conjure up some coordinates to go directly from into B, but we have these body frames, so we need to use them. One thing we can do is we can do a little bit of symbolic vector addition. So consider this. I can actually take this position vector P into B and I can break it into pieces. What if we write it this way? P into B is P into A, right? And then from A to B. Similarly, P into C is P into A plus P A to C. We could, if we wanted, we could have said P into A plus P A to B plus P B to C. That works as well. What if we did this? What if we put another point here at the other pin joint? And what if I said P into C is equal to P into D plus P D to C? Any of these are valid. They're all correct. And as long as you go through and you put the correct terms, right, for each one of these, and as long as we can see those terms on the diagram, you've done it correctly. So the one I'm going to do is actually these two. All right. This is actually a good thing to write down. This is showing the grader, it's showing me that you know what you're doing. And also, once you have declared something, so for example, once you have declared P into A, you can now just write P into A, and you don't have to rewrite it repeatedly. So really all that we need to do now is we need to come up with the position vectors A to B, and then A to C. And if we have these, and we have this one, clearly we can just take these and literally add the two vectors together to get the total. So which one of these two are easier, A to B or A to C? Well, look at how we set up our frames. I did the x hat B axis, the direction x hat B is going straight from A to C. So how about we put, let's say from here to here, and we can call that one L2. Why not? You don't have to, everything doesn't have to be in perfect order, right? So L2 is cropping up in the position vector for C, that's okay. So what is PA to C? Well, the distance is L2, and the direction is X hat B. All right, what should we do for PA to B? Well, notice that the direction from PA to B is not conveniently in one of these axes. We could, and this is something you can do, you can, if you want, go through and put in another frame. And we could call this B prime. We could call it the D frame. We could call it the J frame, anything we want. You can create as many points and as many frames as you want, as long as anything you put on the diagram ends up getting defined and backed up. Now, I will do that sometimes when I think it's necessary. In this case, I actually don't think it's necessary. Consider, if we do call this the D frame, what is the difference between the D frame and the B frame? Really, it would just be some angle, and that angle, that's the Greek letter phi, that's not a 0. So I'm saying there is some angle there, and that angle is fixed. And there will always be a fixed angle between the B frame and the D frame because they're attached to the same rigid body. And that rigid body doesn't deform. If body B rotates, then both B and D frame rotate with it. And of course that rotation's just got a fixed angle between them. So I don't think that we need that in this case. So I'm actually going to take it off and I'm going to show you how we get by without it. All right. Consider that, imagine you're driving your car and you are currently in this place and you want to get to this place, and north is this way. How do you get from here to here? We don't define some new coordinate system. We would just go a little bit east and then we would go a little bit north, right? And if we wanted to get to this place, we would go a little bit east and then we would go a little bit down. Same thing if we were going over here, we go a little bit west, a little bit north, a little bit west, a little bit south, right? So what are we going to do in this case? We've got this B frame, and if we want to get from A to B, we just need to go a little bit in the X hat B direction, and then a little bit in the Y hat B direction. Now, we're not going to go L2 in the XB because that would take us all the way to point C. We need to go about that much, and let's call that L3, and then we need to go that much, and we can call that L4. Now, if your diagram starts getting very busy, feel free to draw multiple diagrams. You could do one diagram for just points, another diagram for just frames, however you need to break it up. So what's our position vector then? A to B. In this case, we would say L3 XB plus L4 YB. And that's it. Those are the position vectors. If you want to, you could go back and write the complete position vector for each of these. We could say, for example, I could, having defined all of this, I could come back and I can say now, all right, let's say that, let's do P into C. I can say that P into C is L1 X hat A plus L2 X B. Now that position vector is in two different frames, right? I've got a little bit in the A frame and a little bit in the B frame. This is perfectly acceptable. There's no problems with doing that. As long as all of these frames and all of these distances are defined, everything's okay. Before we move on, how would we have done it? How might we have approached it if we went from the position vector from N to D to C, just as an academic exercise? Let's do that one. All right, this time I'm going to say that P into C equals P into D plus P D C. So what are these then? P into C equals, and I'm just going to write these underneath. Well, first we need to go into D. Let's say that there is some horizontal distance and there is a vertical distance between them. These are both pin joints. These points don't move. So the horizontal and the vertical distances are both fixed. We've done through L4. So there's L5 and there's L6. So the first part of the position vector gets us from N to D. We need to go L5. In what direction? Well, these don't move. That means we can use the inertial frame. So this is L5 xn plus L6 yn. This right there, that is just P into D. Next, PD to C. So we need the length of the body C, so L7. So if I write down L7 x C, let's pause just a moment. Is that correct? Well, looking at the diagram, notice how we defined the x at C direction. I defined x at C pointing from C to D. This time we're going from D to C, which means we're going against the x at C. And since we're going against it, that makes this position vector negative. Another way that you could look at that is we could say plus L7 in the negative x hat C direction. You could do that if you want, and then you're effectively just bringing the negative sign out. All of these are acceptable. There's all kinds of ways to construct your position vectors. Just remember, the big key here is that whatever you do in the math, it has to always be true, and any variable or frame that is used here must be on the diagram. You must show the grader, you must show me what you're doing. All right, last thing I'd like to do, recall that we're going to do, we want location descriptions, right? So we're keeping track of all these points now. The other half of the location description is the rotation. So last thing we want to do for this problem, I'm going to erase this stuff, and then we just have to define what these frames are. So we have three moving frames. We have A frame, B frame, and C frame. We have to give descriptions for the rotations of those frames. Let's do that now. If you recall from last time what we did for the frames, we need to make diagrams. Now, let's start with the A frame. A frame, and I'll even draw the angle here. Let's say that that's x hat n axis, right? I can draw it as many times as I need. There is some angle of rotation from x hat n to x hat a, and we're going to call that theta 1. Even though I've drawn theta 1 over here, even though I can see that there's a little angle, on your homework, on your exams, I need you to draw this diagram. It just so happens that in the diagram, the A frame is in quadrant 1. It doesn't actually matter, and we'll see that in a bit when we do C frame. But in these diagrams, the easiest thing for you to do is to just do quadrant 1 repeatedly. It doesn't matter what's going on in the diagram, just do quadrant 1 because the math ends up being true regardless. There's x hat n, there's y hat n, that's a terrible n. There we go. X A and Y A We've done this diagram before, nothing has changed. Here's the angle, theta 1. Once you've done the diagram, what do you do next? Next you list all of these projections. So XA equals Y hat A equals, and Z hat A equals. The easy one in this case is the Z. Remember, we're doing simple rotation, right? So there's a Z axis coming out, and these frames, the A frame is rotating about that shared Z axis. So ZA is in fact Zn. And then we did these definitions last time. So x hat A is equal to cosine, and I'm going to put the 1 on it, cosine theta 1, x hat n plus sine theta 1, yn. This one is negative sine theta 1, xn plus cosine theta 1, yn. All right. So you have this. What do you do next? Well, what is this description we've just written? This is the rotation. This is defining the rotation between the N frame and the A frame. Since we have P into A from before, and we have the rotation into A, we put those things together and we can make the location description for A, and it's just the combination of those two things. There we are. Now, and of course, this location description is just bookkeeping. It's just ensuring that you have gone through and you have defined these two things. That's all it really is. It's just a reminder that you have to keep track of these. Now, how different is it going to be to define the rotation for the other frames? Well, let's say that we want to do the location description for B, and we've already done the position vectors to B. We just need the rotation defining B. So we go back to our diagram and we say, okay, we're no longer going to A frame, now we're going to B frame. And here's theta 2. Okay, we're going to do some comments about that though. Sit tight for just a minute. I'm going to do a second diagram, and let's see if we can spot the difference between them. X, B, Y hat B, this is theta 2. All right, in example number 1, all I did is I took that diagram from the A frame and I just, erased and dropped in the B's. One thing interesting here is look at how theta 2 is defined. Theta 2 is defined as the angle between x hat n and x hat b, which is just what we did with the A frame. It just happened to be theta 1. In the second case, there. This time, theta 2 is defined as the angle between XA and XB. And that is not the same thing as the angle between XN and XB, because XA moves and XB moves. So imagine if XB is moving, right, and XA is fixed. Okay, that's fairly easy. If XA is moving and XB is moving, then theta 2 then becomes it becomes a function of the motion of XA as well, right? So this is more of a relative angle, whereas this one would be, we could call this an absolute angle, right? Now, which one of these should we do? I'll show you the rotation description for both of them. One of them is easier, one of them is better. The first one, the absolute angle, is easier. And it's easier, which we're going to see, especially when we get into velocity. When we get into velocity, you're going to see that this is absolutely easier. And we're going to come back and we'll touch on it again, and we'll do the more difficult one with velocity just to see what happens. In this case, this absolute angle you end up only having to take care of this one theta. If you use these relative angles, when you get down into the subsequent frames, the B frame, the C frame, the D frame, etc., what's going to happen? Well, you're going to end up with multiple angles in the same expression. The math gets a little bit more complicated. Now, that makes this one easier. However, this one is better. And when I say better, really what I mean is that it allows you to do more complicated problems. If the only thing you ever learn how to do are these kinds of absolute angles, then the only problem you'll ever be able to work is a two-dimensional problem. If you want to be able to do three-dimensional problems, if you are interested in any way in working in actual machinery, things like robotics, airplanes, right? Things that have a lot of motion to them in 3 dimensions, this is what you end up using. And the reason there is that, for example, let's just pretend my arm is a robot. If my arm is only moving in the plane of this whiteboard, then you can go directly from, let's see, here's our little robotic arm. There you go. So here's a whole series of joints in your robotic arm. And if you're using absolute angles, okay, let's see, there is A, B, C, so there is X, D, and we need the angle between X hat N and X, D. There it is. There's theta 4. Now, the problem is with this, if you're in 3 dimensions, what happens when one of these joints spins out of the board maybe? If I take my arm and I bend it at the shoulder, okay, that's fine, we're still planar. And then what happens if I flip my wrist? Or if at the shoulder I rotate my arm? Now you can't go directly from X hat N to this X hat D because maybe X hat D is pointing out, right? Once you get into complicated rotations, these absolute angle definitions, they don't work anymore and you can't use them. So if you want to work in actual problems, relative angles are the way to go. Here's another point. In this example of a robot, if you're going to control the robot and you want to, let's say this is some kind of gripper, and you want to send this gripper and you want to pick up an object, you need to know where it is, right? You need to know, okay, so right now the robot's here and I need to move it a little bit more, and then I need to turn the wrist this way and I need to move it a little more, then I need to drop it this much. Oh, hey, now we're there. How do you know where the robot is? It requires, at the bare minimum, a handful of sensors. A very nice, expensive robot, maybe you've got cameras on it as well. But what kinds of sensors do you have? If we want to know the orientation of this second body, we're going to put a sensor at this joint, and that sensor is called an encoder. Now, encoders are going to return angles at the joint, right? You're going to ping this sensor, and it's going to come back and it's going to say, oh, the current angle at this joint is 47.8 degrees. And this is probably encoder number 2. Because you've got encoder number 1 at that joint, and you've got encoder number 3 at this joint, etc. You ping all of these encoders and you get their current angle measurements. When you do that, when you ping this encoder number 2, it does not return this theta 2. It returns this theta 2. That sensor is going to measure the angle between the first link and the second link. And that's this one, right? Because if the first link moves and the second link stays the same, the data coming off encoder 2 doesn't change. And yet the orientation of the XB axis will be changing. Imagine this first link rotates. That means the second one goes with it, right? So the real world value of the orientation of this body right here would be changing, and yet your sensor data is not changing. So there's a handful of reasons why this relative angle is a better tool. Now, what are we going to do in this class? There will be times where I will use relative angles. By and large, especially when we get into velocities, I'm actually going to use these easier ones, absolute angles. And the reasoning there is just because it's faster. And just because in this little undergraduate course, we're only going to be doing mostly two-dimensional problems. If you want to use relative angles, I am going to periodically use them, and I'm going to show you how and show you what the difference is. But for now, well, moving forward, because we're actually going to carry both of these into the next discussion for just a moment. But moving forward, I'm probably going to use these absolute angles more. All right. So for the next part, we want to, we've got these diagrams and we need to come up with some descriptions. So what would the angle or the rotation description be if we're doing absolute angle? Well, it's actually going to look almost identical to what we did for the previous one, for the A-frame. We need to say that XB equals and YB equals and ZB equals. Of course, ZB is the easy one. ZB equals Zn. Note that we could have also said ZA. And then these trig terms, this is cosine theta 2 now, x hat n, sine theta 2, yn minus sine theta 2, xn, and cosine 2, yn. All right, so this rotation, this would be, let's take these off just momentarily. This would be the rotation from N to B, and this is using specifically this definition of the rotation. Theta 2 is going from N to B directly, and thus we define the B frame with respect to the N frame. Now, what if we had decided to do the relative angle? The difference is that we would no longer define B in terms of the N frame. Instead, we would define B frame in terms of A frame. And you can leave that one as N if you want. We know that Zn, Za, Zb, they're all the same thing. In this case, if you do this, if you use this relative angle, then this rotation, it was into A, now we're going A to B. Which one's correct? This one or this one? They both are. Either way. Consider that the diagrams are different, and these terms are different because they're going from different angles, and then the way we call it out is different, but it's all consistent. So when you work your problems, you just have to keep it consistent. You show me, you show the graders that clearly this is how you're setting up the frames, this is how you're defining them, this is what you're calling them, and then this is what you put into the location description. Either way is acceptable. So what's going to happen with C-frame? Well, you have the same choice with C-frame. C-frame you could measure as an absolute angle. We could go N-frame directly to C-frame. And instead of theta 2, this is now theta 3. We could go from, this time we could go from the B-frame to the C-frame. XC, YC. And this is theta 3. You have your choice, relative angle or absolute angles. Maybe in some problems there are cases where you might need to mix and match. In general though, if you're going to use some absolute angles, use them throughout the whole problem. If you're going to do relative angles, use them throughout the whole problem. Of course, the relative angles is how we do it in professional problems. Anything 3 dimensions, you have to use these. Okay. There is actually one more thing that I want to do before we close up for this video. So you've got all these positions, you've got all these rotations, right? You can combine them into those location descriptions. What are we going to do with this? What's the point in calling all this stuff out? Why do we care? Let's use the example of the position vector that we did from N to point B. So going back, P into B was P into A, and then PA to B, and we said that was equal to L1 XA plus L3 XB and L4 YB. All right. What if we're building some machine that's going to, let's say it's using an industrial process, and mounted at point B is a welding tool. And we have designed this mechanism such that we can put a little electric motor at this, and it's going to apply a little bit of torque, and this thing's going to move back and forth, and it's going to move that welding tool in some very specific locations to do some welding on a car part, maybe, right, on an assembly line. And since this thing is it's just a machine and it's all automated, we can hit those exact same points very precisely. And we can do it every 47 seconds, right? A new part comes in, bang, 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 weld, weld, weld. That part rolls out, another one rolls in. We need to know then, where is point B? Where is the welding tool? But we don't need it in A frame and B frame. I need to know where that point is in the real world space, in the space of the actual factory. So it's all done with respect to point in. We know that there's some assembly line behind this, and we can get our measurement tools out or whatever, and we know where the part is going to be with respect to point in as well. So I just need the real world position of B. That means I need, or I want, P into B, and I'm going to put an in right there. Now, I'm not going to use this notation very often, but when I do, what this means is it's like we're forcing this position vector into the in frame. That means we need it specifically in that frame. So I don't want A frame or B frame. I want everything in the in frame. So what do? P into B. Well, this distance of L1, this distance doesn't change. So I'm just going to write down L1. And what we're going to do is we're going to get rid of XA, and we're going to replace it with something else. And what do we replace it with? Well, we've been writing down all of these descriptions of the different frames. And go back and look at how we defined X hat A. We said that X hat A was cosine theta 1 xn plus sine theta 1 yn. And you can distribute the L1, and I'm sure some of you have been looking at this and you already recognize that that's what it is. If you want to know, and this is just P into A, right? Like we still got some other parts to add to it, but the position of A is the distance multiplied by the cosine in the x direction, and the distance multiplied by the sine in the y direction. Maybe this seems silly that we went through this much trouble just to get something so obvious, right? I assure you this is useful. It is perhaps not so necessary when you're doing these simple little two-dimensional problems. And this is a simple problem. This is absolutely a simple problem. But when the problems get more difficult, and absolutely when they become 3D problems, this is how you have to set it up. Next, plus L3, and we can do the same thing for XB, right? Plus L4, and we can do the same thing for YB. Now, here's one example of where relative and absolute angles are going to make a difference. This definition that I have written over here, this was still for the relative angles, because look how B is written in terms of A, right? So if I take this and I put it here in this block, let's do that. Cosine theta 2 XA plus sine theta 2 YA. Remember, we want this in the in frame. And what I've just done is I've taken a position vector in the B frame and I put it into the A frame. And if we wanted to, we could go and we could replace X hat A, right? We could turn that into its own expansion, and we could take Y hat A and we could turn that into its own expansion. If you're using relative angles, you end up having to just sort of chain through all the different frames, D frame to C frame to B frame to A frame to N, and it gets a little tedious. Obviously, if you're doing it by hand. If you're using software tools, then all of these transformations just end up being a couple of lines of code. But you can't write the code unless you know what you're doing, right? And you have to be able to go back and check the math in the code anyway. So this is an example where relative angles become more complicated because you have to roll through all the different frames. If you're able to go directly from the B frame to the N frame, then this becomes very fast. If instead of doing this relative angle, we had done absolute angle, then these are all in terms of N already. And then now, this is all we had to do. And for the next part, we're replacing YB. Well, here's the definition of YB, so I'm going to take this and I'm going to bring it down. Minus sine theta 2 xn plus cosine theta 2 yn. Okay. So, all of that just to show the usefulness of the rotations and how we have to keep track of positions and orientations. This process right here, I do not expect you to take all of your position vectors and put them into the N frame. The only reason you would have to do this is if I ask you to do this, or if you're working some kind of problem where you need to know what is the real world position of point B in the X and Y coordinates of this inertial frame. There's a part or a generator or a transmission line or something, right? There's something over here, and this has to be somewhere with respect to it. That means you need to know where it is in the inertial frame, and you would do this process. Okay, I think that's it for this video. We're going to do a couple of more in the next couple of days. We're going to keep talking about positions and orientations, honestly, the entire semester, because it's a part of every single problem. We're not always going to do everything in this much detail. And definitely once we get past the first exam, I'm going to assume that you're able to do this without me listing out every detail. So I hope that helps. You've got some homeworks that you need to be working on, and I will see you next time. Best of luck.